Okay, so welcome to our first video presentation of the year. This begins Unit 1, the Science of Physics, Lesson A, What is Physics? So in this lesson what we're going to be doing is just kind of talking about the nature of physics, its related fields and activities. We're going to talk about the scientific method real quick and discuss the use of models in physics. We're also going to just kind of go into some measurement stuff, talk about what's called the SI units or metric units, scientific notation, significant figures, that kind of thing, and see how they fit in with physics. Our targets, our learning targets then for this unit are to be able to identify activities and fields that involve the major areas within physics. We want to be able to describe the processes of the scientific method, and you want to be able to describe the role of models and diagrams in physics. At the end of section 2 of this video, we're going to be focusing on listing the basic SI units and the quantities they describe, converting measurements using metric prefixes, distinguish between accuracy and precision, and then use what's called dimensional analysis to convert between systems of measurement. So if you've been through chemistry, some of this could be a little bit of a review for you. Otherwise, we're moving right on into the physics after this. Okay, so what are the topics that we cover in physics? I like to say that the physics is kind of the rule book of the universe. Okay, what we do is we look at phenomena, physical phenomena we see in the universe, and try to come up with the simplest explanation of it. Okay, everything around us can be described using the tools of physics. Okay, the goal of physics is to use a small number of basic concepts, equations, or assumptions to describe our physical world. Okay. And these principles can then be used to make predictions about a broad range of phenomena. For example, physics principles that are used to describe the interaction between two planets can be used to describe the motion of a satellite orbiting the Earth. Okay, so some of the topics then that we cover in physics. We start out covering what's called mechanics, which is motion. Okay, mechanics is the study of motion. So we're talking about things that are falling. We talk about friction. We talk about weight. We talk about forces. Those kinds of things. After that, we're going to move into other types of topics like thermodynamics, which will be heat and temperature. Okay, vibrations and wave phenomena. So the way waves move and what all that means. We're going to talk about optics, which is the study of light, things like mirrors, lenses, color, that kind of thing. We'll talk about electromagnetism. We'll talk about relativity, and hopefully we'll be able to get to talking about some quantum mechanics as well. So each of these major physics topics play a role in something as common to us as the operation of a car. Okay, you look at a car, thermodynamics, engine, getting us efficient engines and using of coolants and things. Electromagnetism, getting your battery and your starters, your headlights. Optics are in your lights and your mirrors, and vibrations and mechanical waves. Those are like your shock absorbers in the car, radio speakers, sound insulation from the outside environment, and then of course mechanics is obviously involved in a car. Car moves. Mechanics is the study of motion. So physics is really everywhere. We're surrounded by the principles of physics in our everyday lives. Okay, we'll easily be able to see that. So anytime we go into a science class, we always begin with talking about the scientific method. What is that? That's just a way that we go about solving problems in science. We start by making observations, then and collecting a bit of data. We plan, and we end up with a question. We want to answer that question, so we come up with a way to test to see if our answer to that question is correct. And then we interpret those results and revise that hypothesis if we have to. So we also, throughout the development of the scientific method and throughout trying to solve problems, we come up with models that can be used to explain certain phenomena. Take, for example, this picture of this basketball. So say we want to study what's happening here, but we only want to study the motion of the basketball. There's all kinds of extra things happening in here that we could look at. We've got all the players down here. We got a player here. We could talk about, there's all kinds of observations we could make, but really all we want is the motion of the ball itself. So what we do is we isolate then the ball from all that extra information that we don't need, and we focus our study on just the motion of the ball. So as we go through our study of physics, we're going to use models that simplify things we're looking at. We're going to ignore things about situations that are not going to affect the final outcome. And by simplifying those situations and using models, we'll be able to make useful predictions about how the physical situations are going to work. Okay? And what we can do is we can use these models to help us build hypotheses and simplify those situations. Okay? And then those models will help us guide experimental design. An example of how this works is with Galileo. Galileo, he modeled the behavior of falling objects in order to get a hypothesis about how objects fall. Okay, at the time when Galileo published his book, it was believed that heavier objects would fall faster than lighter objects. So he created kind of a mental model to try to talk about whether that would be true or not. So he imagined two objects of different masses tied together and released at the same time, such as two bricks of different masses, right, tied together. So if we were to do that, and say we were to place the lighter brick above the heavier brick and drop them at the same time, the lighter brick would be pulling up slightly on the heavier brick, and the heavier brick would be pulling onto the lighter brick. And if objects fell based on their mass, that is, if heavier objects fell faster than lighter ones, then when you tied them together, they would fall at a rate somewhere between the two objects on their own, right? Or say, for example, turn them the other direction, right, and put the small brick on the bottom and the heavier brick on the top. You would think then, if the heavier things fell faster, then the heavy brick would overtake the smaller brick and pass it up on the way down. But that's not what happens, okay? And so by using a model, then Galileo was able to show that objects fall at the same rate. So the point here is that we're going to be using models to help us to describe situations, make sense of them. They're going to help us simplify situations. They're going to help us build hypotheses and help us guide experimental design. And the kinds of models that we're going to be using is we'll use mathematical models. Okay, we'll use thought-type models like Galileo used here, and others that we'll see as we move along. Okay, so one of the things that we have to do in science in order to be able to talk about the things we're looking at is we have to talk about measurements. Okay, we have to measure things, and when we have to measure things, we have to have a standard measurement system. Okay, in physics, the standard measurement system we use is called the SI system. It stands for International System of Measurement, and there are three primary units of measurement that we use, right? For measurements of length, we're going to use a meter. That's our standard unit, is the meter. A lot of time we're going to see things in kilometers, right? So we're going to see a problem or a situation where we're measured something in kilometers. If we want to use our mathematical models to solve that situation, we're going to have to convert kilometers to meters. We'll look at how to do that here in a moment. The meter then is, originally the standard of the meter was a certain distance from the equator to the North Pole. Currently, the standard of a meter is the distance traveled by light in a vacuum in 3.33564,095 times 10 to the negative 9 seconds. Okay, so that is how we define a meter. Then we've got the kilogram. That is our standard unit of mass. Okay, this current standard definition of a kilogram is the mass of a specific platinum iridium alloy cylinder it's kept somewhere in England or France, I believe. And then our standard unit for time will be the second, and our definition of the second is a certain amount of times the period of a radio wave emitted from a cesium-133 atom. Okay. So the SI system, international system, is really sometimes considered the metric system. They're very, very similar. Okay. So it uses metric prefixes in the measurements that it makes. Okay. For example, we'll be using millimeters and centimeters and kilometers. Okay. Here, primarily, those are the kind of the primary. But there's other prefixes that we'll see as well. We'll see micro. We'll see nano. Possibly pico, and they go as small as femto, atto, and as large as exa. Okay, but generally speaking, you'll see prefixes from milli, centi, deci, and kilo will be the primary prefixes that we see. So what do those mean, right? All it means to do any kind of metric conversions is you're just moving a decimal point. Okay, this is one of the things that we have to get good at in order to be successful in this class. Okay, we're just moving a decimal point, right? So this is probably something that you should copy down in your notebook right here. We start out, say we're talking about a distance measurement or something, and we're given a measurement of 15 kilometers. Okay, 15 kilometers. In order to solve a problem, we have to convert the kilometers into meters, right? So down here at the bench, this is where we put our meters, right? Our seconds, and our grams. Okay. Now, usually with our mathematical models, when we're talking about a mass, our mathematical models work with kilograms as our mass. Okay, so if we're given something in grams, we have to convert it to kilograms. Whereas if we're given a distance in kilometers, we need to convert that to meters in order for our mathematics to work. So how do we do that? If we have 15 kilometers, we're sitting up here at kilometers. We want to get down there. We got to take 1, 2, 3 steps down. We move our decimal to the right. So if we're going down the staircase, we move our decimal to the right. Moving up the staircase, we move our decimal to the left. So 15 kilometers is the same as 15,000 meters. It's as simple as that. So we need to practice this. You need to get accustomed to using meters, kilograms, and seconds as our standard units in all problem solving. So let's look at a problem, right? We have a typical bacterium has a mass of about 2 femtograms. Okay, we want to express that measurement in terms of grams and kilograms. Well, if we look at our table here of our metric prefixes, right, we see here's femto right here. It's 10 to the negative 15. What that means is we need to move the decimal 15 places depending on where we are on our staircase, right? So femto is a small number, right? It's a small prefix. So it's down here at the bottom of the staircase. It's 15 steps from grams right here in the middle. So what we'd have to do is we'd have to take 2.0 and move the decimal point 15 places to the left, right? So that's going to put us a lot of zeros on there, right? So an easy way to do this then is to change 2 femtograms into grams, is we're going to use what's called scientific notation. Okay, and we're just going to simply write 2 times 10 to the negative 15 grams. Okay, and that's right there. There's our answer right there for changing 2 femtograms into grams. Now it asks us to change it into kilograms as well. Okay, so now that we're in grams, it's a simple move to change it to grams, right? So if we look here, we're here in grams. We've got 2 times 10 to the negative 15 grams. All this number means is this is a number that we've got the decimal point moved 15 places to the left from where it is right here. So now we want to move this 2 times 10 to the negative 15 grams to kilograms, which is 3 places up the staircase. So if we're moving up the staircase, we're going to move our decimal to the left. Well, if you think about this, remember our original femtogram started way down the staircase, okay? So it's not even pictured there. And then we got to grams by going up 15 steps, right? So we've got to go up 3 more steps. So if we start from our original femtograms, right, and we go up to kilograms, how many steps is that? Well, that's 18 steps. So to write this in kilograms, it would be 2 times 10 to the negative 18 kilograms. Okay? So at this point right here, what I want you to do is I want you to stop the video. You've got your notebook. I want you to do in your reading packet on page 14, is practice 1A. I want you to do number 1 and 3 in your notebook before continuing on with the rest of the video. Okay, so our last topic for this first video is accuracy and precision. When we're making measurements in physics, we want to be accurate and precise in our measurements. What we mean by accuracy describes how close a measured value is to the true value of the thing being measured. So, say for example, we want to know the height of a table. We want our measurement of the height of the table to be as accurate to the actual height of the table as we can get. We also want our measurement to be precise. And precision refers to the degree of exactness with which a measurement is made and stated. Okay. So, for example, we've got the pencil right here. Okay. An accurate measure of the pencil would get us as accurate as possible. It's kind of the rules then for dealing with accuracy in measurement. When say we're measuring this pencil here and we zoom in on it, we see that the pencil is 10 centimeters almost to 18.5 centimeters, right? So it's some distance in between here. So what we would do is we would report this measurement as 18 centimeters right here. We couldn't go all the way to the half because, as you can see, the pencil does not quite get to the 18.5 centimeter mark, right? It gets somewhere in between that, but we can't tell with any accuracy exactly where that is. Okay, so we would say that is an 18 centimeter long pencil. Okay. And then precision kind of refers to the degree of exactness with which the measurement is made, right? So a measurement that both accurate and precise is right on the mark, right? When we have low accuracy, low precision, we're all over the board. We have here low accuracy but high precision, right? We were aiming for there, we didn't get there, but we didn't get there every time, okay? Here we've got high accuracy, we're almost there in our target, but low precision. And then finally here we've got high accuracy and high precision. Now, if you've been through chemistry, chances are you may have heard something about significant figures in there, and in your reading packet it talks about significant figures. Really all I'm looking for as far as that is significant figures helps us to keep track of imprecision in our measurement. Generally not going to hold people to the rules of significant figures, but certainly do want you to be as precise as possible in the measurements that we make. So generally speaking, as far as significant figures in our calculations go, round answers to about 2 decimal places. That's what I can say about that. All right, so that ends our presentation, our first video presentation, and make sure you read through the the reading as well. Take good notes and come up, answer your summary questions, and we'll see you in class.